good afternoon, or good evening, depending on where you are in the world. Thanks for joining us for our webinar presentation today entitled 5 Tech-Savvy Ways to Measure Flow in Places You Never Thought Possible. I'm Janice Landsfeld. I'm a product manager here at SonTek, and the side lookers that we're going to mostly focus on today are a product that I manage.
I'm Brittany Jenner, and I'm in technical support, but for the past 6 months I've been working on the development of the new SL.
And Brittany is the most technically savvy person with the new SL. So what we'd like to cover today is this. It's a pretty timely topic, I find, side-looking Dopplers in general, and I'll tie them together with the webinar topic. But first we're going to just discuss some general advantages of side-lookers and then get into the 5 specific obstacles that we're commonly seeing in the field these days. You know, here at SonTek we don't develop instruments in a vacuum, and we take a lot of feedback from customers and use that to inform how we develop our hardware and software. So as I go through this list, you know, this is all feedback that we've seen in the field. And applying particularly to side lookers, we're going to be talking about some unpredictable, complex flow conditions. We'll have some specific examples. We'll try to do a good job of showing a little bit of data, a little bit of real-life installation examples, some application stories. We're going to mix it up a bit and just show how side lookers, which are sometimes subject to difficulty when water level changes, can be handled better with some new technology. We're also going to talk about some of the improvements in the housing design, which allow us to fit into smaller, narrower situations than ever before. We're going to talk about some of the improvements that make it even easier than ever before to keep, maintain, and if necessary, service a remote site. We are going to talk about a perennial problem with instrumentation, whether it's Dopplers or anything else, which is sedimentation and fouling. And lastly, slow and reversing flow, which is a much bigger deal for hydrologists, irrigators, water managers. There's some technology improvements that can capture that better than ever before. So with these common obstacles, we often see these, or combinations of these. People may or may not be aware of some of the existing solutions and now some of the new solutions that the new SLs bring to the table, so that things that you might have thought before were not feasible or otherwise too costly, well, maybe they are now. So we'll walk through some of these examples and perhaps get you thinking about that. So first of all, I just want to catch everyone up. I know we probably have a lot of different experience levels out there. So we'll just catch everybody up on what a side looker is in general. Here's SonTek's family of side lookers. I have them arranged there in order from lowest frequency here on the left. This is our 500 kilohertz. Our mid-range, which is 1500 kilohertz, and our shortest range system, which is the 3000 kilohertz system. And some of you who are familiar with our instruments in the past might notice that these two on the left look dramatically different from our previous instruments. These are an all-new design. They have an all-new shape. We're going to take advantage of this camera and show you some models so you can see what the new systems are about. And so this is an example of what a side looker is commonly used for. You have it mounted on the bank of a river or a canal. It can be a natural stream. It could be concrete lined. It could be a pier. But the instrument is fundamentally looking horizontally across a water body. And if desired, that horizontal beam can be broken up into cells or bins, as many as you like, well, or up to 128 for the new models. If you want that kind of resolution, or anywhere in between, 1 to 28. And at the same time that that's going on, a side-looking Doppler also has a vertical beam that's detecting the water level. So from these fundamental measurements of horizontal velocity and water level. We can put those together to give us flow and total volume, as well as velocity and water level. And users use one or a combination of those parameters to get the data that they need. So like I mentioned, you can mount the side looker in any number of ways. Down here on the left, I have an example of a port and harbor application or a coastal application where you might have a long-range system looking out into a harbor or a bay. In the middle there, I show a concrete line channel. What I like about that picture is that it shows how different users come up with ways that fit their particular application. In this situation, the user came up with this. They came up with this protective shield to prevent the instrument from getting damaged by debris. And then on the right there, it's a good picture of our slide mount. That's one of the biggest advantages of a side looker, and it's just in a natural river there on a natural bank. You can put a structure like that and make it easy to slide the instrument up and down. And we'll cover more about some of those specific mounting examples later on in the presentation. So before I launch into some of the exciting features, I want to mention that the long-range version, that is the Argonaut SL 500, has not changed. So it's still the long-range option for a side looker. If there is any doubt about what the specs are or which instrument is right for your application, please refer to our brochure and the spec sheet that's on the back. It's very thorough. It documents very cleanly, I hope, what the differences are. And there's a little cutout you can see on the bottom there. In summary, the SL500 has some features that go for longer range, perhaps even saltwater solutions. So, for example, the cable is still wet-mateable. It has a compass sensor as well, and at the same time, it also still requires things that are original to the Argonaut. So things like the Argonaut software, the Argonaut flow display, for those of you who use a Modbus protocol, it still uses all of those Argonaut things. So that's just wanted to make sure people understand when we start talking about some of these new features that they apply to the SL 1500 and the 3000. SL 500 still good for those long-range solutions. When in doubt, again, consult the brochure or give us a call here at SonTek or your representative. So before we continue on, I just want to point out some of the general advantages of side-looking Dopplers. Again, I think this is a timely topic. We keep tabs on what people are telling us in the field and what users are doing, what they're encountering, what their difficulties are. And more, I'm hearing managers as well as users just concerned about ease of access and the buzzword safety first, whether you're getting into the water yourself or you're a manager who is in charge of people who are getting into the water. You want to make sure that's done as safely and as quickly as possible, and obviously side lookers that are easily accessible minimize the chances of people getting into the water and dealing tools and whatnot. And along those same lines, since you can access a side looker from the side, you don't have to worry about hiring divers, dealing with replacing underwater batteries, hiring a boat, and so on for maintenance. Again, you can access it from the side. You don't have to interrupt your plant operations if, for example, you're an irrigator delivering water or you're a hydropower operator delivering water for plant operations. The side looker, again, is just off to the side, no worrying about access. And again, water delivery, if you have to make sure that those data are online for your clients or stakeholders, in and out, if you need really quickly, if you need to service something, no interruption. And in some cases, if you're a researcher, for example, or you're doing some hydrologic modeling, maybe you do want a horizontal profile, and that's ideal for your situation. A horizontal profile, of course, being a profile that starts on the left bank and then goes to the right bank. as opposed to a bottom-up profile. So again, those are some of the general advantages of side-looking Dopplers, and I list here on the right more of what I'm seeing out there in the field that I think are particularly timely applications for the side looker. For example, hydropower, whether it's really fine-tuning delivery and supply and operational requirements to make sure the plant is running at an optimal way, or just in general to do structural evaluation over time. More and more, unfortunately, we see things on the news about floods and natural disasters, so flood warning systems are more and more important. Irrigation, of course, especially out here in California, scarcity and disputes and litigation need to be resolved, and they need data in a very timely manner. And then just good old-fashioned hydrological discharge monitoring. Increasingly, data are on the web for everyone to see. Everybody wants to see that live data in real time, and it has to be accurate. And the users who are in charge of those instruments are held accountable. So for all these reasons, I thought this was a very timely topic. So let's get into some of the specific obstacles that I know some of us are experiencing out there in the field, perhaps right now. We'll be going over first, this is probably going to be our longest, most complex obstacle, and we'll offer 4 examples, a river example, an irrigation example. We'll talk about velocity indexing in general, which relates to complex flow, and then I'll give a flood warning example. So with that, I'll hand it over to Brittany to talk about our first example.
All right, so this first example, as Janice said, is a river example, and it's in the UK, so it's actually a canal here. And on the left side, you can see we've got an Argonaut installed. This is an Argonaut SL 1500. And then below that is the new SL 3G 1500. This is during some of our beta testing of the new unit. So we wanted to look at this site in particular, what was happening because there are floodgates. And so that creates changes in stage, which can create some complex flow conditions. So here I'm showing on the top graph, we've got stage, and below that is the X and Y velocities. The X velocities are the dark blue, and the Y velocities are the light blue. And you can see in the velocity data, you see this broad increase here in the X velocity, and then again here. And that's also shown here with the stage data increasing here, and then again increasing here. So these are 2 major floods. So these are sort of the large-scale observations we can see from the data. And then we can see these smaller scale changes in stage as well as the velocity. And those smaller scale changes are the floodgates downstream trying to regulate how much flow is going into the canals even further downstream. And so the new SL and the Argonaut as well are able to capture these large-scale changes and small-scale changes all at the same time. So the second example is an irrigation canal, and this is from Yuma, Arizona. We've got the SLs installed over here on this bank. And then you can see here is a remote boat, and there's an acoustic Doppler profiler on there. This was, again, during some of our testing of the new instrument. So we were collecting very high-resolution velocity profiles along the reach of the canal so that we could make sure that our algorithms for calculating discharge just from that horizontal profile, we want to make sure those were accurate. So this is a bit complex. It's a lot going on this screen.
Don't worry, we'll break it down for you.
So let's just break down, first of all, what SmartPulse is.
Yes. So as I mentioned, the new SonTek-SL, the 1500s and the 3000s, come equipped with SonTek's patented SmartPulse HD. HD stands for high definition. So here's just a little bit of background. I don't expect too many people out there to be acoustic experts. That's our job. But we're going to just briefly run through what SmartPulse does. Back in the day, there are broadly 3 different acoustic processing techniques: Pulse-Coherent, Broadband, and Incoherent. And back in the day, any one instrument would use any one of these 3 techniques. And there are different manufacturers who use different techniques or different instruments designed for specific application to use those techniques. But just to really, really broadly summarize it, each technique had its niche that did one thing really well. So pulse-coherent processing, for example, was really good at handling slow water velocities, but at the same time, it was limited in the profiling range it could cover. So if, for example, you had to measure really high water velocities, or with a really long and/or at a really long profiling range, pulse-coherent was not the best technique to use. In fact, it might have even been impossible to use. So in that case, you would probably want to choose an incoherent technique. You might sacrifice some of this lower range, though. And then broadband kind of hit a sweet spot in the middle, but it still didn't handle some of the higher velocities and higher profiling ranges of incoherent. So what SmartPulse does, now that SonTek has the capability of using all 3 techniques in one instrument, and the algorithms, in other words, the smarts inside the instrument to switch among techniques, we don't have to be limited by any one of these techniques. We can use all 3, depending on how fast the water is going, or how deep the water is, or even some of the turbulence factors. So as water conditions change, you don't have to be out there deciding which technique to use. The instrument will do that for you and deliver the best data under any condition, which I think I just said here. So being that it will handle any condition, specifically with the SmartPulse technique, we can handle slow and low flow, reversing and tidal flow, really low scattering conditions, even better than before, flashy, changing conditions, unsteady conditions, and scientific and hydraulic studies in particular could take advantage of some of the high-resolution data that can come out of the new instruments. And I just have an interesting little graphic here that shows what the original Argonaut electronic set looked like inside. It's true to say that the Argonauts, among ADCPs, were actually pretty small and compact to begin with, but as technology evolves, as electronics evolve, just like your smartphone evolves and gets smaller and smaller and more capable at the same time, SonTek instruments have done the same. So you can see the electronic set in the new instruments is even smaller than before, but smarter, more capable, with faster processing power than ever before. So we can do all of these things and handle more conditions than ever before. So with that background, I'll let Brittany continue.
All right. So I'm going to walk through each of these different graphs here. So on the top graph, we've got X and Y velocity. The dark blue here is the X velocity. The light blue is the Y velocity. And then plotted over on the right, I've got flow, which is shown here in red. So as expected, flow matches up with the X velocity pretty well. And then in the middle, on the right side here, I've got depth, and that's in the red. So we can see there's these changes in depth. And then on the left here, I have the standard deviation of the X and Y velocity, and we can see that changing. So this is, as I mentioned, an irrigation canal, and they've got gates. They've got a gate downstream that's controlling the flow to different irrigation canals. And we installed the instrument on a Friday and then picked it up on Monday. So it's just basically a long weekend. And you can see that the depth initially drops, and that's corresponding with a low velocity at the beginning. You can also see it's right here, right? Yep. Okay. And then as depth starts to increase back up, we can see velocities also increase. And you'll also notice, so we see this step in the velocity. You also see this step right here in the standard deviation, and that's attributed to the fact that the instrument is initially using the broadband technique and then switches into the incoherent technique because velocities have increased, so it's beyond that sweet spot, and it needs to switch into incoherent. And of course, these standard deviations are going to change depending on the method you're using. So you can see right here where water levels are starting to flatten out, and so velocities decrease, and the instrument's trying to decide which is the best method to use. And it's doing this all on its own. We left it out there for the weekend. We didn't have to tell it what method to use. It was on the fly, detecting the velocities, the water level, and figuring out the best possible method to use. And then the other thing that we found, because we also had an Argonaut SL there installed, was that the Argonaut standard deviation was always greater than the new SLs, and that was regardless of the method that it was using.
So our next example to hit on complex flow conditions is not so much of an example, but just something I wanted to mention. Some of the hydrologists out there in the audience know that it can be a pretty complex process, so I'm not even going to attempt to get into it very much. But I did want to point out that one of the major uses of the side lookers is in continuous discharge monitoring, and the way you fine-tune a continuous discharge instrument is through velocity indexing, and I just wanted to point that out to some of our users. So first of all, I wanted to explain the difference and make sure we're all on the same page about what these two different kinds of instruments are. Now, whether you're using an acoustic instrument like from SonTek or a mechanical meter, instruments can roughly fall into two categories when you're talking about discharge measurement, and that would be instantaneous here at the top and continuous down here at the bottom. So an instantaneous discharge measurement means that someone is out there at the site, they're manning an instrument, they're taking velocity measurements and calculating flow as the instrument or the person moves from the left bank to the right bank and the right bank to the left bank. So the point of this kind of measurement is to know accurately at a snapshot in time what the discharge is, ideally through the use of multiple profiles. And one example is the SonTek M9 that does that very well with high resolution. So that's an instantaneous discharge measurement, snapshot in time at a certain water level at a certain condition. But you can't have someone out there 24/7 operating an instrument, going through that many batteries and so on. So if you want to continuously monitor, you put an instrument out there either on the bank or mounted on the bottom looking up, and the instrument is out there 24/7 sampling on an interval perhaps every 15 minutes. In the case of a side looker, now you're not getting this nice profile all the way across. You're getting one slice of the water column. In the case of a side looker, you're getting this horizontal slice. And then there's calculations and extrapolations being made to fill in the rest of this water, so to speak. So you're not getting that full profile, and so at any snapshot in time, the continuous measurement instrument won't be as accurate as your instantaneous measurement instrument. So the velocity indexing method allows you to take data from multiple stages and multiple flow conditions over time, develop a rating based on that collected data, and then from that develop curves and coefficients that you can feed back into the continuous measurement instrument like the SL. And through the indexing procedure, the SL coefficients can be refined and fed back into the SL. So this is a living process. And I know some of the hydrologists out there might be rolling their eyes at that simplification. It actually can be a complex process. So SonTek, we kind of pride ourselves on helping you out with that application expertise. We still offer our FlowPack indexing software. It's a standard feature with all SLs, and it walks you through in a sort of smart page-like fashion, step by step, through each step in that indexing process and guides you through the data inputs. and the SLs do output a file that's easy to import into the FlowPack software. So we like to make that as easy for you as possible. And of course, if you have further questions on this whole process, we're happy to help out, and we have other references about it. And on that note, too, I see some questions coming in. Please, if some of you are familiar with the webinar format, but if you're not, you're able to type in questions as we're talking on the side of your screen. So please don't hesitate to keep those questions rolling in, and we'll try to get to as many as possible before the presentation is over. Because we mentioned ADCPs just a second ago, for example, the M9, I did want to point out that they are a useful tool that go hand in hand with the side lookers, as you just saw. They do have their advantages, too, that help you collect data in other previously impossible places. This is just one quick example of a flood condition where we were able to collect data that there were no data ever before during a flood condition. And again, because of that SmartPulse technology, one thing the M9 does really, really well is go from shallow conditions to deep on the fly without any user intervention, and switches techniques and cell sizes and whatnot to give you the best resolution at all times and to get into those flooded areas, for example. But that's another webinar for another time. If you have more interest in that, let us know. Type that into your question and comment box, and we'll do a webinar on that perhaps. So lastly, this isn't so much of a data example as an application example where perhaps you've seen this before. It was on the Discovery Channel, in fact, about Kuala Lumpur and their need to measure and manage flow during flood systems, during flood events through the city. And they built this incredible network of tunnels and canals to take floodwater through the city. And in the case of the tunnels, there were even roadways, in fact a double-decker roadway that went through this tunnel, and they needed to monitor what the water levels were at any given time instantly. And if those water levels were changing, their managers had to know instantly. So what they did was choose a combination of uplooking Dopplers. The original shallow water uplooker here on the left is what they used, but the new modern version of the uplooker is the IQ here on the right. It's an analogous instrument. In the case of an uplooker, it was mounted here on the bottom of the tunnel, and if floodwaters were rising, we would know in an instant and with great accuracy what was going on, so the city managers could manage that flow responsibly and open and close the tunnel, for example. And then for the channels, the open channel flood delivery system, they chose the original SonTek-SL. And I have a picture here. Some of you might be familiar with the original SonTek side looker that became so popular when it came out back in 1997. And we don't offer that form factor anymore. We have the new slimmer form factor, but that's essentially what it would look like. And for the open channel, that's what they used. And I will hit upon this a little bit later, but if you watch the Discovery Channel episode, which we have on our YouTube, you'll see that it was integrated into this vast monitoring network with monitors and instant readouts, and the new SLs can handle any kind of output you need to integrate into a flood warning system. So along the lines of flood warning and how we handle those large or rapid changes in water level, I did want to point out that the new side lookers do something that nobody else does, which is adjust the beam on the fly for the velocity beams on the fly for changes in water level. So those of you who are familiar with side lookers know that they can be more subject to changes in water level. And that's, we'll get into a little bit more of acoustic theory, and I promise you that'll be it for the webinar. But basically when we send a beam out horizontally, there's a main lobe that measures your velocities, but then there's also a little bit of excess energy. In the case of SonTek, it's not that much, but it is still some. And you don't want to have these side lobes grazing the top or grazing the bottom of the of either the surface or the bottom before the the main lobe gets to the other side. And where these lobes will hit, particularly the top lobe, is dependent on this water level. So if the water level drops, you could be subject to some contamination. So in the past, we would recommend that you situate your instruments, always keeping in mind what your possible minimum depth will be, which is still very good application advice. And I did want to point out that the new side lookers, however, go one step farther. And as the water level drops, if you're getting beyond a reasonable, what we call aspect ratio, so if there's any risk of these side lobes hitting the surface as the water level drops, the instrument is smart enough to pull the velocity profiling beams back to a safe level. And then if the water level rises, we can extend those again. And the net effect, of course, is that you get the cleanest data possible under changing conditions. Okay, so we handled all the complexity there, and we're going to move on to main obstacle number 2, which is, well, what if your river or stream or canal cross section is just too narrow? Should that limit you from installing a flow measurement instrument or velocity measurement instrument? Well, maybe, but probably not. In the past, you might have had to worry about that, but the new side lookers, as you probably just surmised from the pictures, are our slimmest design yet. And we actually have, I'll go through real quick just for comparison's sake. It's more revealing in person what the evolution has been over time. This was the oldie but goodie that came out in 1997. It's, again, small for an ADCP, but it still has had its form factor. And then when we revised the housing, you'll notice we specifically designed it for side-looking operation. So it was meant to be mounted on the side with this built-in mounting plate, much slimmer form factor. Yet, we have improved on it even more. Mm-hmm. It's even slimmer. I dare say it's about 2 inches in thickness. Even the 1500 is pretty slim. And the 3000 is, yep, just a little over 1 inch in thickness. So the SL3000 has the smallest cell sizes of any Doppler out there. You can get down to, side-looking Doppler. You can get down to 4 centimeter cell sizes if you need. So, for example, if you did want to collect data really close to the bank here or really close to the pier, pulling in the instrument design allows you to collect data even closer to the structure or the bank than ever before, and getting those smaller cell sizes means you can get a profile closer to the bank than ever before. So if you need that high resolution data close to a structure, or if you're just trying to fit into a narrower situation, one of these two new side-looking options, you'd be hard-pressed to say it won't work. Or ask us for a demo. We'll give you one. You can tell us. So what if that's not your problem, but what if your site is remote and you just know from past experience that, getting out there to service the site, do the installations, have a risk of something going wrong is just going to be too much work, too much time, too much money? Well, we do know that field work is field work. It takes time, it takes expertise, and with that in mind, we have added many new features to the new side lookers, and we're just going to run through some of these and show you that, well, maybe it's easier than you thought to keep up a site. One of the most notable features of the new side lookers is that they feature both an acoustic water level sensor and a pressure sensor. It's kind of hard to see, but there is a port down here in the front that houses the pressure sensor. So not only are these redundant sources of water level, which they are, but they also are smart, and they continually talk to each other and inform each other of what's going on. So for example, the acoustic sensor, as long as it's detecting a surface, knows what the water level is and can subtract out, we can infer the atmospheric offset, apply that to the pressure sensor with every single sample. So in other words, there's no drift. There's no drift in the pressure sensor due to atmospheric offset. And here's some data that Brittany collected and put together for us.
Yeah, so you can see the dark green in the top is the vertical beam, and it stays fairly constant. And I've also plotted this dashed line is the pressure sensor. And you can tell that it's drifting. It's been installed for a while, and
there's nothing wrong with this data. It's just normal.
It's just what happens. Atmospheric conditions can change, and so your pressure sensor will start to read a little bit off from your vertical beam. But what we've done with the new SL is that, as Janice explained, they're talking to each other. And so you can start to see right here, I've got the lighter color is pressure from the sensor. And it starts to drift here, but it uses the vertical beam to recalibrate itself and take out that atmospheric pressure, and you start to see them line back up again. And that's without having to go out to the site. It's doing that all on its own.
And again, we know field work is field work. We know things will happen. So for example, if there is debris that snags on your instrument, if the vertical beam is blocked, sometimes that happens, well, at least the pressure sensor is always calibrated, so to speak. So you know that that's reliable data to fall back on if you have to. Hope it doesn't happen often, but this is just one example of how that water level data, which is so critical, is even more robust than ever before. And should save you some time from having to go deal with, water level cutouts, for example. So we're going to hit that the rest of my list with one single page, which kind of shows the beauty of this new SmartPage software that we have. We'll walk through each of these one by one. So unlike something like the Argonaut, which although is very good, robust software, we can, with our new SmartPage for the third generation systems, just start at the top. Those of you who are familiar with the M9 River Surveyor Live software know that there's this SmartPage feature that gives you feedback. It's interactive. As you properly set up the instrument, you can just go from top to bottom. These little icons will turn green if you're ready to go. If it advises you maybe you should check something, it's yellow. Or if there's something that needs attention, these icons will be red. So just with the SmartPage, you go from top to bottom, and then you're done. So here on the right-hand side of the SmartPage, it's kind of hard to read, I know, but this says View Live Data. So unlike other instruments, with the new SL, when you go out to the site, and say you just want to check something, everything's working fine, you're just doing your regular maintenance, you just want to see some data, don't have to stop the instrument, you don't have to change protocols, don't have to unhook anything. Just keep the instrument running, hit the View Live Data button, and you will see live data. Same thing if you want to go out to the site and just download your data. Nothing's wrong. You just want to get in, get out quickly. There's a download data button. No need to stop data collection. Just download your data, make sure everything's clean, leave. Right here from just from the SmartPage, you can see what your recorder status is. And we have increased the recorder status, the recorder life significantly to 4 gigabytes. That's a lot of space. If necessary, you can go longer time without having to go out to the site to do your download. And then when you get to the end of the SmartPage and are done with your setup, unlike other instruments, unlike even our previous instruments, changing protocols from, say, a binary or a serial ASCII or a Modbus solution or an analog solution, it's all done with one button from the SmartPage. Just click a button, change it. And once your protocol is set, again, for example, say you're in SDI 12, if you just want to go download your data at the site, there is no need to stop data collection, no need to change protocols. Just come up here, do your download, hit the live data button. This is an example of what the software pop-up screens look like. Just no need to change protocols, make sure everything's okay, and just get done quickly.
Yep.
I think this is a significant improvement.
Absolutely. And one of the, advantages to that is that sometimes if you have to stop data collection to download, you might forget to start data collection again,
yes.
Or you might accidentally change a setting, or something might go wrong. But now
you might forget to change the cable hookup for SDI 12.
Right. Yep. No more jumper. So yeah, you don't have to stop it. You can just download data and move on.
All right. So what if? So say, yeah, okay, it's feasible to get out there, but Mother Nature still doesn't want to cooperate. Sedimentation and fouling or both, one or the other or both, are still going to make it impractical or impossible. Well, yes, it is a problem. No, we can't wave a magic wand and make trash go away or make weeds stop from forming, but I did want to hit home on this point one more time, simply because it is so important. What has made side lookers so popular? I have on the left here a picture of a bottom-mounted system. This was an original shallow water bottom-mounted system. This is what it looked like when one of our customers went out to the site, covered in trash. Someone has to put on their boots, go out there, clean it off, make sure it's working. It would be great if an acoustic signal could penetrate through this, but it can't. Similarly, knowing your site is very important. This isn't so much of a technical support presentation. Again, write your questions down if you have specific questions. We'll get to them, but know your site, know if sedimentation is going to be an issue, know if fouling is going to be an issue. In this case, barnacles were a problem, even on side lookers. Just because it's side looking doesn't mean barnacles aren't going to grow on it. But I have another slide that shows some solutions to that just aren't possible with bottom-mounted systems. While we're on the topic of barnacles and sedimentation, I would like to point out that you'll see barnacles perhaps growing on the transducer face here, or you might see sediment building up on top of an acoustic transducer. That doesn't necessarily mean your data are bad or wrong. This is one of the advantages of Doppler systems. As long as this obstruction is fixed, you probably will see some loss in signal strength. But as long as that signal still gets out there, the velocity data could very well be fine. So don't assume that your data are bad just because your instrument has some stationary sedimentation on it. Now, if there's grass or something moving around in front of it, of course that will affect the velocities. But yeah, just let's not forget one of the main advantages of Doppler systems there. All right, so even though you might have sedimentation, even though you might have fouling, at least if you're using a side looker, you do have easy mounting, easy access, easy cleaning, and easy preventative maintenance. By the way, this is not an example. We're not telling you to let your system look like this, but if you did, if you're taking over for the last guy, at least you can pull it up, at least you can bring it up onto the dock, clean it off, bring a bucket of an acid solution over, soak it for a while. Just not have to worry about hiring a boat, for example. So here's an example of, again, 3 generations of side lookers. They've always been good at being mounted, whether it's a natural condition, doesn't have to be concrete lined. If you have a concrete lined canal, that's great. But you can install these mounting systems anywhere. You can even, again, create some sort of protective structure for it. It can be a slide mount that moves up and down diagonally. It could be a vertical mount. It's kind of whatever your individual situation requires. It takes a little bit of, again, knowledge of your site and some creativity to figure out what solution is best for you. Or call us and we'll be happy to advise. Oh, I wanted to point out too, anti-fouling paint is an option. And if you have an interest in that, we have recommendations in our manuals, or again, just give us a call. So the bottom line is you don't have to do this with a side looker. You don't have to hire this guy to get suited up. Or even if it's you who's getting suited up, you're going to have to put your suit on. You're going to have to get your dive buddy or your tender. You're going to have to get your air. You're going to have to fill out your paperwork to make sure you've complied with your agency regulations. It's going to take a good half a day to do the simplest of maintenance on a bottom-mounted system. And all of that takes time, it's going to take money, and it's going to just take a lot of extra work every time you do it. So whether you're doing it yourself or your manager, it just really complicates things in a hurry. All right, moving on to, so what if we get through all of those obstacles, but still, maybe you've tried it in the past and the flow is just too slow for previous instruments you've tried, or you're not sure if it'll handle reversing flow? Well, we have some examples of that that might get you thinking about those applications in new ways.
So the first example is a tidal channel where, of course, we have reversing flow, and as it's reversing, it's slowing down to the point where velocities are near zero, and sometimes even zero. And so for this example, we've got an SL 3000 3G mounted next to an Argonaut SL 1500. So different frequencies.
Oh, do you want? I forgot to mention the mounting plate. Do you want
that's right. Yeah. So you'll notice that the SL, the 3000.
This is the 3000.
Yeah. It's and the footprint is the same as the SL 1500.
If you would like to use the mounting plate.
Right. And we've got it right here. Yep. And it matches up with this guy. So easy enough if you've got if you're pulling down your Argonaut 1500 for some reason and you're putting in a new SL3G, you can use the mounting plate and it'll fit just as the old one did. Mm-hmm. So here I'm showing the velocity data from the Argonaut 1500 on the top. The X velocities are in red and the Y velocities are in blue. And then below that are the data from the SL 3000. The dark blue is the X velocities and that light blue are the Y velocities. And you'll notice I've got the scales set the same. So the 3000 is showing a smaller magnitude than the 1500, and that's just because the 1500 is profiling further out into the channel and capturing the larger velocity towards the center. But regardless, both of them show that nice tidal signature, and you can see the velocities are reversing and, of course, slowing down to zero. And both of them do a great job of capturing this. So the advantage of the new SL is the standard deviation of the X velocity. And this is really important in these really low flow environments. Yep. So the Argonaut reports standard error, which we can easily calculate the standard deviation from that using the number of pings. And this Argonaut was using tower pings, so we just multiply the averaging interval times 4, and that will that'll allow us to calculate the standard deviation. So I've down here below, I'm showing the standard deviation for the new SL. And from my calculation of the maximum standard deviation from the Argonaut, and this is just the X velocities, that's what we're usually most concerned about, we can see that there's an order of magnitude improvement with the new SL. And these are both using the same ping method. They're both incoherent, which, as we pointed out before, that method will change your standard deviation, but I just wanted to point out that they're both using the same method, and we see a significant improvement in the standard deviation.
Significant. Yep. Which becomes much more critical for those of you who are measuring really low velocities and slow flows.
Right.
So don't have data, but just wanted to point out this is not a side-looking application. But on the topic of handling reversing flow, Dopplers in general are really good at this. And I just wanted to throw this in there because here in California, and those of you who don't live here probably have heard about the drought conditions that we're subject to. And so this is a very timely example of how we in California have to get really creative with how we manage our water. And in this particular example, in a normal year, when there's normal deliveries of water, there's a main canal and a canal company that delivers water to an end user, which is an irrigation district. And the irrigation district sends that to its customers. But in a drought year like this, there's different water allocations going on. People are getting creative. People are selling their water differently. So this year, the irrigation district is reverse pumping some of their groundwater into the main canal for delivery out. So for the first time ever, they had to measure reverse flows, and actually didn't know at the outset that there was a way to do that accurately, which of course you have to do when you're managing and even pricing water with this much precision. So in this particular case, a SonTek IQ-Pipe, in this case mounted to the top, right here. Here's the instrument and the transducers right here. And being a Doppler, it will measure flow in both directions. Very timely example right here in California. All right, our last example.
Yeah, so we wanted to show an example of what the new software is capable of. So we're showing your typical time series. We've got velocity on the top, and then on the bottom graph is SNR. And, oftentimes you have to figure out what's happening at your site. Why are there changes in velocity, or why are there spikes in SNR? So this is, like I said, the typical time series. But with the new software, with the new SL3Gs, we have color maps and the ability to plot several more variables all at once. So this is just one sort of screen grab of what you could look at in the view data window. And you could look at up to 5 time series with 2 variables on each side. We've got the tabular data down at the bottom, and then we've also got this new profile plot on the right. And you can turn any of these off. This is a bit cluttered.
If you're not a super user like Brittany, it may take some time to decipher this. But
yeah, and the really powerful thing here are the color maps. And you can change the color scales on these. You don't have to use these primary colors. You could change these up. And you can also set your min and max colors. So at the top, I'm just showing the time series of SNR. And then in the background of that is the color map of SNR. And you'll see that it's darker towards the bottom of that plot because that's closest to the instrument. And
each of these is a profile. So at any
right.
point in time, this is the closest part to the instrument,
Mm-hmm.
and then this is the farthest point from the instrument.
Yeah.
And a whole time series of each profile.
Okay. Yes. And you'll notice that the SNR, as you'd expect, is slowly decreasing as you move away from the instrument. And you can visually see the SNR better than just that single average point that we see in time series. So in the middle graph, we're showing a speed color map with the darker greens being higher speed and the lighter greens being lower speeds. And then on the right side of that, I've got the time series of velocity, the mean velocity here, and we see a drop in velocity down to 0, where the color maps indicate lower speeds. So it's just another way to visualize that. And then in the bottom graph, the color map is direction. The light blue is one direction, and the darker blue is a different direction. I think they differ by almost 300 degrees there. And then on the right side in red, I've plotted depth, and we can see changes in depth. And we notice that we see a step up in the depth right here, and then all of a sudden there's this change in direction in the velocities. And again, this is, one line here is a single profile, and you can see that in one single profile, the water is moving in all sorts of different directions. And then we can see after that, the depth decreases, and then we start to see uniform flow. Water is moving all in one direction. We move into that light blue region. And then again, we see a bump up in the depth, and then the water direction starts to become irregular. So, you know, what could be causing that? It seems like the water is almost hitting a wall and then just like moving back and forth. And we could visualize that. You know, we see that clearly with the color maps, that the water is just moving back and forth with no clear primary flow direction.
And just the resolution that you can even see all of these little changes is what I find pretty amazing.
Yeah.
Whether it's just the resolution here that we get with the water level or just the resolution here with the direction changes.
Right. Yeah.
Well, but a very unusual site.
Yeah,
I wonder where that was.
A whitewater rafting course in the UK. So this probably isn't where you typically install your side looker, but we were doing some testing initially, and this was.
The guys in the UK like to have fun and
yeah.
really put the instrument to the test. And of course, there's a lot of man-made changes and abrupt changes and different things going on in the water. So it's just an interesting place to get some data and really see what some of the capabilities were.
Yeah.
So if you want to try that, go right ahead. So with that was our last example. Just going to summarize real quick what we reviewed. Hopefully we went over some specific obstacles that maybe you're seeing out there, and then some of what the solutions were. In other words, so for unpredictable complex flow, we offer on-the-fly changes perhaps with SmartPulse and self-adjusting water level. With a too narrow or too close to the bank you're trying to measure. New SL have the slimmest design ever and the smallest cell sizes down to 4 centimeters. If you think getting out there and dealing with the site on a regular basis is too time-consuming, well, there's lots of new features and software features that enable you to do those field sites much more quickly. Sedimentation always has been, always will be, much more easy to deal with an SL, and the new SLs even accommodate the original mounting frame. And then slow reversing flow. Hopefully we showed you a few examples there of how, well, probably better data than ever before, and you might want to give it a try. So we're getting to the end of our presentation, and just wanted to remind everybody that SonTek.com is a real wealth of information out there. If we didn't get your questions answered, we're going to get to some in a second, but there's plenty of information, brochures, spec sheets, white papers. If you want to geek out on SmartPulse, we have a SmartPulse tech note you can download. And if you're out there in the field, there's 24/7 emergency tech support, so give us a call if you need anything. And because you registered for this webinar, we're also going to send you today's PowerPoint. And then for everyone who registered also, we're going to write down all of these questions, which we have on little pieces of paper. We'll type them out, give everyone the answer, and send that out to everybody. So with that, we'll get on to the questions. And if you want to envision us sitting here at SonTek, we're right behind this tree, behind this window, answering your questions. And below this is the team that supports us and you out there in the field, from everyone who makes the instruments, to enters the orders, to repairs them, to buys the parts. That's all of us right here. All right, lots of questions. I don't think we're going to get to them all, but we have time for a few before the hour is up. I know one question out there is, can you turn SmartPulse on and off? And the answer to that is yes. We know some people out there are doing velocity indexing for good reason. You might want to control as many variables as possible. You might want to use SmartPulse, you might not. You might want to try it out till you're ready to switch over. So if you do want to use the new SL and keep it in the standard Pulse Incoherent mode, you can do that. It's just a checkbox in the software.
Oh yeah, so a question about the blanking distance. The blanking distance has not changed for the SL3000. It's still 10 centimeters, and for the SL1500, it's 20 centimeters.
But again, the profile, the instrument profile is slimmer, and the cell sizes are smaller. So although the blanking distance hasn't changed, you can get data closer to the instrument.
Right.
Yep. got a question here that says, what is the minimum depth needed for installation? That depends on a few factors. It depends on the frequency of the instrument that you're using, and it also depends on how far across the river or the canal you need to profile. Because again, remember that slide where we showed this side lobe, possible side lobe interference. If your channel is really wide, you're going to need to, that horizontal beam is going to need to reach farther across the bank, and it's going to, as it does that, it's going to spread. So you're going to need more depth if you're trying to reach farther. But the minimum depth is 10 centimeters, I believe. I can pull out a spec sheet if necessary. Again, no, it's what it's on a spec sheet, but in real life, you're going to have to determine how far you need to profile. There's a rule of thumb on SonTek instruments that we like to say 20:1 is a safe aspect ratio. Again, you have to always be cognizant of what's going on at your site, but our side lobe suppression is pretty good. So that means if you have a foot of water above or below the instrument, 1 foot, you can go out 20 feet. And generally, you're going to be okay. Again, just always be cognizant, though, and give us a call if you have any questions.
Another question that's come in is, how do they perform in freezing conditions? So the instrument itself does have a temperature spec and cannot be left out if you expect the water to freeze over. So we'd recommend that if that's going to happen, you should pull it out and remove it for the season.
Now, having said that, if you know the instrument is going to be submerged, if the instrument is mounted at depth and there's ice on top, the instrument could still, it's not going to be damaged. You'll probably have to do some indexing and apply your own flow equations to it. But as long as it's submerged, it's going to be okay. The reverse question is often asked, can I leave the instrument out dry?
Right.
And I mean, the short answer is yes, you can. And as a matter of fact, the new instruments, you'll notice it's kind of a lighter color. They handle heat pretty well, and they can be left out dry. The instruments, actually the new ones, we didn't hit on this in the slides, but the instruments are smart enough to know whether or not they're in water. Mm-hmm. So if they're not in water, they'll revert to a very low ping rate just to keep tabs on where they're at if there is water. If water comes back, they'll go back into a sampling mode. So the instrument has a lot of features built into it that handle those dry conditions well. Now, having said that, it's always a good practice. If you know it's going to be out there for a long period of time, just bring it in and just take good care of the equipment. Yep. So many questions.
I know.
Some our time manager is going to cut us off soon, but we'll get to a few more. What determines if the beams fall back or not? It used to be SNR. The original Argonauts do use SNR, and we still do that. So I'll let Brittany cover, but there's another one that we hit on, so we'll just summarize that again.
Right. Yeah. So, and this is something that was always being done by the Argonauts, but now this is something that you can turn on and off with the new SLs in case for some reason you just wanted to get the data out there, even if it was bad. Sometimes you want to see that. So in addition to the SNR filtering, it also uses the aspect ratio, which essentially just means it's using the depth to figure out if it needs to pull the beams back, because again, you don't want the side lobe interference with the surface or sometimes even the bottom of the channel.
Right. So before we had one criterion, which was the SNR. Now we have two.
Right.
We use the SNR and the water level. Okay, we're going to take one more question, and we're going to answer this one because apparently there are a lot of you asking about this. Questions regarding the T-shirts that Brittany and I are wearing. And we just decided to have a little fun with the new instrument and the new capabilities of it going in shallow water, more places than ever before, and more complex conditions than ever before. In other words, the new side lookers will boldly go where no SL has gone before. So in that spirit, we're honoring a TV show that used that motto. All right, everyone, we have a lot more questions here. Thanks for participating, and thanks for bringing your questions to us. we'll get these all typed up. We'll get them all answered, so don't worry. We'll get back to you on these. Thanks for joining us, and let us know how else